Hello everyone. Today we'll study the graph of polynomial and rational functions. First of all, let me show you how to graph polynomial functions. Graph each of the following polynomials, indicating the X and Y intercepts and end behaviors. First example, f of x is x minus 2 times s plus 3 times s minus 5. How can we graph this polynomial function? Let me show you step by step. First step, let's find the zeros of this polynomial function first. Find the zeros of the functions first. In order to find the zeros, I set the function equal to 0. First step, set the function equal to 0. Find the zeros of the function. Then once I set the function to 0, I set each factor equal to 0. I get s minus 2 equal to 0, x plus 3 equal to 0, s minus 4 equal to 0. Then solve each equation for x. In the first equation, I get s equal to 2. In the second equation, I get s equal to negative 3. In the third equation, I get s equal to 5. Those are the zeros of this polynomial function. Next, use number line. Use number line test. Draw number line. Next, draw number line. Put these three numbers on the line. Put these three numbers in the line and write it in order. Negative 3 is the smallest. 2 and 5. Put these three numbers on the line. Put the zeros on the line. Now, if I cut the number line 3 times, I cut into 4 regions. Region 1, region 2, region 3, and region 4. If I cut the line 3 times, I cut into 4 regions. Region 1, region 2, region 3, and region 4. On each region, choose a test number for x. On each region, choose a test number for x. In the first region here, every number is less than negative 3. So choose a test number less than negative 3. We can choose negative 4. Those are test numbers. Next region, pick a number between negative 3 and 2. Make it easier, you can pick 0. Next, between 2 and 5, let's pick test number. We can pick 3, make it easier. We can pick either 3 or 4, make it easier. Here I pick 3. Next region, everything here is larger than 5. We pick test number larger than 5, let's pick 6. So, pick test number on each region. Next, plug in test number into function f. Test for positive and negative. Plug in test number into function f. Test for positive and or negative. If I plug in negative 4 here, negative 4 minus 2 is negative. We don't care about the value, we only care about the sign. Negative 4 minus 2 is negative. Negative 4 plus 3 is negative 1, which is negative. Negative 4 minus 5 is negative 9, that's negative. Then multiply together. Triple negative. We know that double negative is positive. Positive times negative is negative. Triple negative is negative. If there are odd number of negative sign, the result is negative. If there are even number of negative sign, the result is positive. If I plug in 0, 0 minus 2 is negative 2, that's negative. We don't care about the value, we only care about the sign. We only care about the sign. If I plug in 0, 0 plus 3 is positive. 0 minus 5 is negative. Then multiply. Multiply together. Negative number times positive number is negative. And then negative number times negative number is positive. If there are even number of negative sign, the product is positive. Next, plug in 3. If I plug 3 into the function, 3 minus 2 is positive 1. 3 plus 3 is positive 6. 3 minus 5 is negative 2. Then multiply. Positive number times positive number is positive. Then positive number times negative number is negative. If there are number of negative sign, the product is negative. Next, plotting 6. 6 minus 2 is positive 4. 6 plus 3 is positive 9. 6 minus 5 is positive 1. Triple positive is positive. Next, let's sketch a graph based on this information here. Let's sketch a graph based on the information here. First of all, the zeros here represent the X-intercepts. The zeros here represent the X-intercepts. So 2, negative 3, and 5, they are X-intercepts. So the intercepts are 0, 2, 0, negative 3, 0, and 5, 0. These 3 zeros, they are X-intercepts. 2, 0, negative 3, 0, 5, 0. For X-intercepts, the Y coordinate must be 0. So here we have 3 X-intercepts. 2, 0, negative 3, 0, and 5, 0. Those are the X-intercepts. Now, if f of x is negative, that means the graph go below x-axis. If f of x is negative, that means the graph go below x-axis. Now, if f of x is positive, between negative 3 and 2, f of x is positive, means the graph go above x-axis. If the function is positive, means its graph is above x-axis. Its graph is above x-axis. If f of x is negative, between 2 and 5, that means between 2 and 5, function f go below x-axis. Between 2 and 5, if function f is negative, that means its graph go below x-axis. Negative, positive, negative. If f of x is positive, that means the graph of function f go above x-axis. That's a graph of the function y equal to f of x. That's a log graph, because we don't know how to find the maximum or minimum. We don't know how high the graph will go. We don't know how low the graph will go. We will learn how to find maximum, minimum in calculus class. Then the graph will be more accurate. This is a rough sketch. The graph looks like this shape. And this graph is not in scale. This is a rough sketch because we don't know how high it's gonna go, how low it's gonna go. We don't know how to find maximum and minimum for now. In calculus class, we will learn how to find maximum and minimum. The graph will be more accurate. For now, that's a rough sketch. Next, how do we find a Y-intercept here? For Y-intercept, we set x equals 0. We plug in 0 for each x. For Y-intercept, we set x equals 0. Plug in 0 for each x. Plug in 0 for x. We get 0 minus 2, 0 plus 3, 0 minus 4. Plug in 0 for each x. Then simplify. 0 minus 2 is negative 2. 0 plus 3 is positive 3. 0 minus 4 is -5. -2 times 3 is -6. -6 times -5 is +30. So the y-intercept is 0, 30. Y-intercept is 0, 30. Next, we try to describe the M behaviors. Next, we try to describe the M behaviors. This graph has two ends, left end and right end. This graph has two ends, left end and right end. Let's describe both endpoints, both M behaviors. There are two ends, left end and right end. On the right side here, you can see that S goes to infinity. 0, 1, 2, 3 go all the way to infinity. On the left side, S goes to -infinity. So for the M behavior, we try to describe the function f as n approach to positive infinity and negative infinity. We try to describe f of x as x approach to positive infinity or negative infinity. So for the M behavior, we say this. As x approach to infinity, as x approach to infinity, function f goes all the way up. As x approach to infinity, function f goes all the way up. So say function f approach to infinity. As x approach to infinity, function f also approach to infinity. As x approach to infinity, function f goes all the way up, which means function f also approach to infinity. On the other side, as x approach to negative infinity, as x approach to negative infinity, what happened to function f? As x approach to infinity, as x approach to negative infinity, what happened to function f? As x approach to negative infinity, as function f, as x goes all the way to the left, function f goes all the way down. Function f goes all the way down, which means function f approach to negative infinity. That's the M behavior of this graph. That's the M behavior of this graph. So in this graph, the S-intercept is 2, -3, and 5. S-intercept is 2, -3, and 5. Put them in order, -3, 2, and 5. Y-intercept is 0, 30. Y-intercept is 0, 30. Since we didn't draw this graph in scale, we don't know how to find maximum or minimum. We can't graph in scale. So we can simply say this point is 30. Y-intercept is 30. This point is 30. We didn't draw this graph in scale. In the y-axis, we didn't draw this graph in scale in the y-axis. So this point is 30. Because we don't know how to find maximum or minimum. We don't know how high the graph will go and how low the graph will go. So we didn't draw this graph in scale in the y-axis. So we just say this point is 30. We don't know how high it is. The y-intercept is 30. Y-intercept is 30. The M behavior, as x approach to infinity, function f goes all the way up, which approaches to infinity. As x approach to negative infinity, function f goes all the way down, which is negative infinity. So those are the intercepts of the function and the M behaviors of function f. Next example. F of x is x plus 1 squared times x minus 4 times x plus 5. In order to graph this function, let's find the zeros first. So for zeros, we set the function equal to 0, then solve for x. For zeros of a polynomial function, set the function equal to 0, then solve for x. If the function is 0, we set every factor equal to 0. here for x plus 1 squared, that can be written as s plus 1 times s plus 1. S plus 1 squared is the same as s plus 1 times s plus 1. If I set each factor equal to 0, I get s plus 1 equal to 0, s plus 1 equal to 0, x minus 4 equal to 0, x plus 5 equal to 0. Then solve each equation for x. I get s equal to -1, s equal to -1, s equal to 4, s equal to -5. Those are zeros of this function f. But here, for these two zeros, s equal to -1 and s equal to -1, they are exactly the same. So we only write it once. And we say this zero has multiplicity of 2. This zero has multiplicity of 2. This zero has a multiplicity of 2 because -1 appears twice. This zero has multiplicity of 2. 4 only appears once. This zero has multiplicity of 1. This zero only appears once, so this zero has multiplicity of 1. S equal to -5. This zero only appears once, so this zero has multiplicity of 1. So this zero has multiplicity of 2, it appears twice. This zero has multiplicity of 1. This zero has multiplicity of 1. They both appear only once. Now, multiplicity can be found from the degree here. Multiplicity can be found from the degree here. When we see x plus 1 equal to 0, when we see x plus 1 squared, when we solve an equation for x, this zero has multiplicity of 2. Multiplicity can be found from the degree here. And for s equal to 4, if I solve this equation, I get s equal to 4. In this factor here, the degree is 1. So now that multiplicity is 1. For this s plus 5 here, the degree is 1. So the multiplicity is 1. So the multiplicity of 0 represents the number of repeating zeros. In general, it changes the behavior of the graph near the 0. In general, it changes the behavior of the graph near the 0. Let me show you an example. Before we continue, let me show you an example first. For example, if a polynomial contains x minus 2, when we solve an equation, I get s equal to 2. So the multiplicity of this number of this 0 is 2. Sorry, the multiplicity of this 0 is 1. This 0 has multiplicity of 1. Another example, if we have x plus 3 squared equal to 0. When we solve an equation, I can take square root on both sides. I get x plus 3 equal to 0. Solve for x, I get s equal to -3. So for this 0 here, this 0 has multiplicity of 2. This 0 has multiplicity of 2. Another example, when we have x minus 4 to the power 3 of 0. If we solve an equation for x, I can take cube root on both sides. I get s minus 4 equal to 0. Then get s by itself. I get s equal to 4. This is a 0. This 0 has multiplicity of 3. This 0 has multiplicity of 3. This 0 has multiplicity of 3. Now, with these multiplicities, it changes the behavior of the graph around the 0 a little bit. For example, at s equal to 2, suppose 2 is here in the x-axis, that's a 0. If the multiplicity is 1, the graph goes directly through the 0. If the multiplicity is 1, usually the graph goes through the 0 directly. Like in the previous example, if the multiplicity is 1, the graph goes through the 0 directly. However, if the multiplicity is more than 1, if the multiplicity is more than 1, when the graph approached the 0, there's a little curvature here. If the multiplicity is more than 1, when the graph gets closer to the 0, there's a little curvature here. It doesn't go straight through the 0. There's a little curvature. When the graph gets closer to the 0, there's a little curvature. It doesn't go through the 0 directly. When the graph gets closer to the 0, there's a little curvature. This 0 has multiplicity of 3. So when the graph gets closer to the 0, it doesn't go through the 0 directly. That's a little curvature. The larger multiplicity, the larger curvature it is. The larger multiplicity, the larger curvature it is. If the multiplicity is 1, the curve doesn't go through the 0 directly. There's a little curvature. In general, if the multiplicity is even, the 0 bounces the curve back. If the multiplicity is even, the curve bounces the 0. The 0 bounces the curve back. If the multiplicity is odd, the curve goes through the 0, but there's a little curvature on the other side. If the multiplicity is even, the 0 bounces the curve back. If the multiplicity is odd, the curve goes through the 0, but there's a little curvature here. The larger multiplicity, the larger curvature it is. So that's how multiplicity changes the behavior around the 0. That's how the multiplicity changes the behavior around the 0. If the multiplicity is more than 1, when the curve gets closer to the 0, there's a little curvature near the 0. It doesn't go through the curve. It doesn't go through the 0 directly. And the larger multiplicity, the larger curvature it is. Those are some examples. Next, let's continue with this example. So in this function, we have 3 zeros, -1, 4, and -5. Next, we make a number line test. For these 3 zeros. Draw a number line. Put the zeros on the line. Write in order from smallest to largest. We have -1, 4, and -5. -5 is the smallest, then it's -1. 4 is the largest. -5, -1, and 4. If I cut a line 3 times, I cut into 3 regions. For each region, choose a test number. For each region, choose a test number. Then try to find the sign for function f. First of all, choose a test number less than -5. We can choose -6. Next, choose a test number between -5 and -1. It could be any number in the middle. Let me pick -3. Next, choose a test number between -1 and 4. Let me pick 0. It could be any number in the middle. Make it easier. Next, choose a test number more than 4. We can pick 5. Then, plug each test number into function f. Here, to make it easier, let me copy function f and put it here. Function f is s plus 1 squared times s minus 4 times s plus 5. Let me copy the function, put it here. F of x is x plus 1 squared times s minus 4 times x plus 5. If I plug -6 into function f, -6 plus 1 is -5. -5 when we square become positive. If I plug -6 here, -6 minus 4 is -10, which is negative. If I plug -6 here, -6 plus 5 is -1, which is also negative. Then multiply the numbers. Positive number times negative number is negative. Negative number times another negative number is positive. So in general, if there are even number of negative sign, the product is positive. Next, plug -3. -3 plus 1 is -2. -2 squared is positive. If I plug -3 here, -3 minus 4 is -7, which is negative. If I plug -3 here, -3 plus 5 is positive 2, which is positive. Then multiply together. Positive number times negative number is negative. Negative number times positive number is negative. If there are odd number of negative sign, the product is negative. Next, plug in 0. If I plug in 0 here, 0 plus 1 is 1. 1 squared is positive. 0 minus 4 is -4, which is negative. 0 plus 5 is 5. 5 is positive. Then multiply together. Positive number times negative number is negative. Negative number times positive number is negative. If there are odd number of negative sign, the product is negative. Next, plug in 5. 5 plus 1 is 6. 6 squared is positive. 5 minus 4 is 1, which is positive. 5 plus 5 is 10. 10 is positive. When we multiply 3 positive numbers, the result is positive. Next, based on this information here, let's sketch a graph. First step, label the 0 on the graph. First step, label the 0 in the graph. We have -1, 2, 3, 4, 5. -5 and 4. 1, 2, 3, 4. Those are the 3 zeros. Now label them. If the multiplicity is more than 1, label the point. Here, -1 has multiplicity of 2. So -1 has multiplicity of 2. Keep it in mind. -1 has multiplicity of 2. Keep it in mind. If the multiplicity is more than 1, it's better to label this point. Now, sketch a graph. When s is less than -6, we see that function f is positive. When s is less than -5, function f is positive. If function f is positive, means it's above x-axis. If function f is positive, means function f is above x-axis. If function f is positive, means it's above x-axis. Next, for x is between -4 and 1. For x is between -4 and 1. Function f is negative. Function f is negative means it's below x-axis. Now be very careful. -1 has multiplicity of 2. If the multiplicity is more than 1, the curve doesn't go through the 0 directly. There's a little curvature here. There's a little curvature and a 0. It doesn't go through the 0 directly. There's a little curvature here. Next, between -1 and 4, function f is negative. That means function f is below x-axis. Function f is below x-axis. And -1 has multiplicity of 2. If the multiplicity is more than 1, the curve has a little curvature at -1. So when function f is positive, it goes above x-axis. When function f is negative, it goes below x-axis. When function f is negative, it goes below x-axis. When s is more than 4, function f is positive, so it goes above x-axis. Here at 4, the multiplicity is 1, so the curve goes through the 0 directly. There's no curvature here. The curve goes through the 0 directly. That's a rough graph. Next, let's find the X and Y intercepts and the end behaviors. For the X-intercepts, look at the zeros here. The zeros are the X-intercepts. The zeros are the X-intercepts. So X-intercepts are -1, 0, 4, 0, and -5, 0. Those are the X-intercepts. Those are the X-intercepts. For the Y-intercepts, we set x equal to 0. For Y-intercepts, we set x equal to 0. Plug in 0 for x. I get 0 plus 1 squared times 0 minus 4 times 0 plus 5. 0 plus 1 is 1. 1 squared is 1. 0 minus 4 is -4. 0 plus 5 is +5. Then multiply, we get -20. That means the Y-intercept is 0, -20. Since we didn't draw the y-axis, in scales, we label this point as -20. We didn't draw the y-axis in scales, so we label this point as -20. That's the Y-intercept. Since we didn't draw the y-axis in scales, this point here is labeled to be -20. That's the Y-intercept. This point is -20. Next, let's describe the end behaviors. This graph has two ends, left end, right end. Let's describe the end behaviors. On the left side, as s approaches to net infinity, we can see the function f go all the way up. On the right side, as s approaches infinity, the function also goes all the way up. So, as x approaches infinity, function f goes all the way up. If function f goes all the way up, it goes up to infinity. F of x approaches infinity. as x approaches infinity, f of x approaches infinity, and as x approaches to negative infinity, on the left side, as x approaches negative infinity, function f also goes all the way up. If function f goes all the way up, it goes up to infinity. That's the graph of function f. So when function f is positive, it's above x-axis. When function f is negative, it goes below x-axis. If the multiplicity is more than 1, the curve has a little curvature at this point, at the 0. If the multiplicity of the 0 is more than 1, the curve has a little curvature around the 0. And when the curve is negative, when function f is negative, it's below x-axis. When function f is positive, it goes above x-axis. That's the graph of function f. Next example, f of x is negative 2s cubed times s plus 2 times s minus 4. In order to graph this polynomial, let's find the 0 first. So set f of x equal to 0. Then solve the equation for x. We first of all set each factor equal to 0. We first of all set each factor equal to 0. Then solve each x individually. In the first equation, I can divide both sides by negative 2. I get s cubed equal to 0. Then take cube root on both sides. I get s equal to 0. In the second equation, I can subtract 2 from both sides. I get s equal to negative 2. In the third equation, I get s equal to 4. I can add 4 to both sides. This 0 has multiplicity of 3. This 0 has multiplicity of 3 because we have s to the power of 3. This 0 has multiplicity of 1. This 0 has multiplicity of 1. Next, use number line test. Use number line test to test the positive or negative of function f. Draw number line first. Draw number line first. Put the zeros on the number line. Make sure to put them in order. Negative 2 is the smallest. Next is 0. Next is positive 4. Put these 3 zeros on the number line. Make sure to put them in orders. Negative 2, 0, and 4. If I cut the number line 3 times, I cut into 4 regions. If I cut a line 3 times, I cut into 4 regions. Then pick test number on each region. On the first region, I can pick test number negative 3. Pick test number less than 2, less than negative 2. Next, pick test number between negative 2 and 0. We can pick negative 1. Next, pick test number between 0 and 4. Let's make it easier. Let me pick positive 1. We can pick 2 or 3, but make it easier. Let me pick 1. Next, pick test number greater than 4. We can pick 5. Then plug test number into function f to test for positive negative sign of function f. If we plug in negative 3, negative 3 cubed is negative 27. Negative 27 times negative 2 is positive. If I plug negative 3 here, negative 3 plus 2 is negative 1, which is negative. Negative 3 minus 4 is also negative. Together, positive number times negative number is negative. negative number times negative number is positive. If they are even number of negative sign, the product is positive. Next, plug in negative 1. Negative 1 cube is negative 1. Negative 1 times negative 2 is positive. Negative 1 plus 2 is positive 1, which is positive. Negative 1 minus 4 is negative 5, which is negative. Together, positive number times positive number is positive, and positive number times negative number is negative. In general, if there are odd number of negative sign, the product is negative. If there are even number of negative sign, the product is positive. If there are odd number of negative sign, the product is negative. Next, plug in 1. If I plug in 1 here, 1 to the power 3 is 1. 1 times negative 2 is negative. 1 plus 2 is 3. 3 is positive. 1 minus 4 is negative 3, which is negative. Then multiply. Negative number times positive number is negative, and negative number times negative number is positive. If there are even number of negative sign, the product is positive. Next, plug in 5. 5 to the power of 3, we know that it's a large number. It's a large positive number. Positive number times negative 2 is negative. If I plug in 5 here, 5 plus 2 is 7. 7 is positive. If I plug in 5 here, 5 minus 4 is 1. 1 is positive. Then multiply. Negative number times positive number is negative, and negative number times positive number is negative. The product is negative. If there are odd number of negative sign, the product is always negative. Next, based on this information, let's sketch a graph. So for the graph, first step, let's label the zeros. There are 3 zeros, negative 2, 0, and 4. The zeros are the X-intercepts. So we have negative 2, 0, and 4. The zeros are the X-intercepts. Let's label the 0 first. Then sketch the graph. We know that when x is less than negative 2, function f is positive. When x is less than negative 2, function f is positive. If function f is positive, means it goes above x-axis. And one more thing, I forgot to check the multiplicity. For number 0, multiplicity is 3. So it's better to label the multiplicity here. At 0 here, the multiplicity is 3. Zero has multiplicity of 3. Unless negative 2 and 4 has multiplicity of 1. Now for the first region, when x is less than negative 2, function f is positive, which means function f go above x-axis. That's the first piece of the function. Next, when s is between negative 2 and 0. When s is between negative 2 and 0, function f is negative. If it's negative, means function f go below the x-axis. Since 0 has multiplicity of 3, the curve doesn't go through 0 directly. There's a little curvature around 0. There's a little curvature around 0. The curve doesn't go through 0 directly. So when function f is negative, the curve goes below x-axis. Next region, when s is between 0 and 4, function f is positive. When s is between 0 and 4, function f is positive, which means between 0 and 4, function f go above x-axis. And 0 has a multiplicity of 3. The graph has a little curvature at 0. doesn't go through 0 directly. There's a little curvature at 0. Next, when function f is more than 4, when s is more than 4, function f is negative. When s is more than 4, function f is negative. If function f is negative, means it goes below the x-axis. And we know that at 4, at negative 2 and 4, the multiplicity is 1. So the curve goes through the 0 directly. The curve goes through the 0. The graph goes through the 0 directly. There's no curvature here. So that's a rough sketch of this function f. Next, let's find X and Y intercepts. The X-intercept is the same as the zeros. Those zeros are the X-intercepts. Those zeros are the X-intercepts. So we have 0, 0, negative 2, 0, 4, 0. There are 3 X-intercepts, negative 2, 0, 0, 0, and 4, 0. From the Y-intercepts, we plug in 0 for x. For the Y-intercept, plug in 0 for x. Y equal to f of 0, which is negative 2 times 0 cube times 0 plus 2 times 0 minus 4. We know that 0 cube is 0, and 0 times every number is 0. So the Y-intercept is also 0, 0. Y-intercept, y coordinate here is 0, and for the Y-intercept, s coordinate is always 0. So the Y-intercept is 0, 0, which is the same as the S-intercept here, which is the same as the 1 of the S-intercept here. This point is also the Y-intercept. Next, let's describe an end behavior. This graph has 2 ends, left end and right end. Let's describe the end behaviors. As x approaches to infinity, as s approaches infinity, as s goes all the way left, function f goes all the way down. So function f approaches to negative infinity. As s approaches infinity, function f goes all the way down. So function f approaches to negative infinity. So f of x approaches to negative infinity. As x approaches to negative infinity, as x approaches to negative infinity, as x goes all the way to the left, as x goes all the way to the left, function f goes all the way up. So function f approaches to infinity. As x goes all the way left, function f goes all the way up. So f of x approaches to infinity. F of x approaches to infinity. That's the end behavior of this graph. Next example, f of x is negative 3 times x plus 3 squared times x minus 1 cube times x minus 5. We try to sketch the graph for this function. So first step, let's find the zeros first. So I set function f equal to 0. Set negative 3 times x plus 3 squared times x minus 1 cube times x minus 5 equal to 0. Then we set each factor equal to 0. We have negative 3 x plus 3 squared equal to 0. X minus 1 cube equal to 0. X minus 5 equal to 0. Then solve for x on each equation. In the first equation, I can divide both sides by -3. I get s plus 3 squared equal to 0. Then I can take square root on both sides. I get s plus 3 equal to 0. Then subtract 3 from both sides. I get s equal to -3. That's a 0. Next equation, I can first of all take cube root on both sides. I get s minus 1 equal to 0. And then add 1 to both sides. S equal to 1. In the third equation, I can add 4 to both sides. I get s equal to 5. So here, in the first equation, we have power 2 here. That means this solution has a multiplicity of 2. This solution has a multiplicity of 2. This solution has a multiplicity of 2. In this equation, we have power 3 here. So this solution has a multiplicity of 3. In this equation, there's no degree here. So this solution has only multiplicity of 1. This solution has multiplicity of 1. Next, let's make a number line test. Based on this 0, let's make a number line test. So draw number line first. Label this 0 on the line. Put them in order. The smallest is -3. Next is 1. The largest is 5. Label the zeros on the number line. And we know that 3-point color line to 4 regions. 3-point color line to 4 regions. 3-point color line to 4 regions. Next, pick test number on each region. Pick test number on each region. First region, pick test number less than -3. We can pick -4. Second region, pick test number between -3 and 0. -3 and 1. Make it easier, let me pick 0. Third region, pick test number between 1 and 5. We can pick 2, 3, or 4. Make it easier, let me pick 2. Next region, pick test number more than 5. Let me pick 6. Then we try to test the positive or negative sign for function f in these regions. Plug each test number into function f. Plug each test number into function f. If I plug -4, -4 plus 3 is -1. -1 squared is +1. +1 times -3 is negative. If I plug -4 into the second factor, -4 minus 1 is -5. -5 cube. Triple negative is negative. It's a huge number, but triple negative is negative. We don't care about a number. We only care about a sign. -5 cube is a negative number. If I plug -4 here, -4 minus 5 is -9. When we multiply 3 negative numbers, triple negative is negative. If they are odd number of negative sign, the product is negative. If they are even number of negative sign, their product is positive. Next, plug in 0. 0 plus 3 is 3. 3 squared is 9. 9 times -3 is -27. That's negative. If I plug in 0 here, 0 minus 1 is -1. -1 cube is also -1. That's negative. If I plug in 0 here, 0 minus 5 is -5. -5 is negative. Next, we multiply. When we multiply, we know that triple negative is negative. If there are a number of negative signs, their product is always negative. Next, we plug in 2. If I plug 2 here, 2 plus 3 is 5. 5 squared is 25. 25 times -3 is -75, which is negative. If I plug 2 here, 2 minus 1 is 1. 1 cube is 1, which is positive. If I plug 2 here, 2 minus 5 is negative 3, which is negative. Then we multiply. Negative number times positive number is negative. Negative number times negative number is positive. If they are even number of negative sign, their product is always positive. Next, plug in 6. 6 plus 3 is 9. 9 squared is 81. Positive 81 times negative 3, we don't know what it is, but it's negative number. Positive 81 times negative 3 is negative. We don't care about the value, we only care about the sign, the positive negative sign. If I plug in 6 here, 6 minus 1 is 5. 5 cubed is a large number, but we know it's positive. If we plug 6 here, 6 minus 5 is 1. 1 is positive. Then multiply. Negative number times positive number is negative, and then negative number times positive number is negative. If there are number of negative sign, their product is always negative. Next, based on number line test, we sketch the graph. Based on the number line test, we sketch the graph. First step, label the zeros. Label the zeros in the x-axis. First step, label the zeros in the x-axis. The zeros are the x-intercepts. So first zero is negative 3. That's the first zero. Next zero is 1. The third zero is 5. The zeros are the x-intercepts. So first step, label the zeros. Next, label the multiplicity for each zero. Label the multiplicity for each zero. Negative 3 has multiplicity of 2. Negative 3 has multiplicity of 2. Number 1 has multiplicity of 3. Five has multiplicity of 1. Next, let's sketch the graph based on the positive negative sign here. When x is less than negative 3, function f is negative. If function f is negative, means it goes below x-axis. If function f is negative, means it goes below the x-axis. Since the multiplicity is more than 1, there's a little curvature here. It doesn't go through negative 3 directly. There's a little curvature at negative 3. Since the multiplicity is more than 1, there's a little curvature at negative 3. It doesn't go through negative 3 directly. Next, when s is between negative 3 and 1, function f is negative, which means function f is below x-axis. And we can see that here, at both endpoints, the multiplicity is more than 1. So there's a little curvature at both zeros. Since at both endpoints here, the multiplicity is more than 1, so there's a little curvature at both zeros. When function f is negative, the curve goes below the x-axis. When s is between 1 and 5, function f is positive, which means function f goes above x-axis. And at number 1 here, the multiplicity is more than 1. So there's a little curvature and a 0. At 5, the multiplicity is 1. At 5, the multiplicity is 1. When x is more than 5, function f is negative. When x is more than 5, function f is negative. So function f go below x-axis. For any polynomial function, the graph is always a continuous smooth curve. For any polynomial function, its graph is always a continuously smooth curve. For any polynomial, its graph is always a continuous smooth curve. That's a log graph of this function. That's a log graph of this polynomial function. For any polynomial function, its graph is always a continuous smooth curve. Next, let's label X and Y intercepts. The X-intercepts is the same as the zeros. The X-intercepts is the same as the zeros. We have -3, 0, 1, 0, and 5, 0. Those are the X-intercepts. For the Y-intercepts, we say x equal to 0. For the Y-intercepts, we say x equal to 0, plotting 0 for x. Y equal to f of 0. If I plug in 0 for x, I get -3 times 0 plus 3 squared times 0 minus 1 cube times 0 minus 5. Then multiply. Plug in 0 for x, then multiply. We get -3 times 3 squared. 0 minus 1 is -1. I get -1 cube. 0 minus 5 is -5. 3 squared is 9. -1 cube is -1 times -5. -3 times 9 is -27. -27 times -1 is +27. +27 times -5 is -135. So the y-intercept is 0, -135. Since we didn't draw the y-axis in scale, so we can label this point as -135. We label this point as -135. So we label the y-axis as -135. That's a rough sketch of the polynomial function f. Next, the end behavior. This graph has two ends, left end and right end. For the end behaviors, as x approaches to 0, as x approaches to infinity, as x approaches infinity, that means as x goes all the way to the right, function f goes all the way down. So f of x approaches to -infinity. On the other side, as x approaches to -infinity, as x approaches to -infinity, function f goes all the way down, which is also -infinity. So f of x approaches to -infinity. That's the end behavior of function f. Next, let me show you how to graph rational functions. In order to graph rational functions, let me first of all show you how to find the horizontal and vertical asymptotes. Here is the steps of finding horizontal asymptotes. Let f of x be a rational function in the form of f of x equal to p of x over q of x, where p of x and q of x, they are both polynomial functions. Let m be the degree of p of x, and let n be the degree of q of x. Degree is the highest exponent in the polynomial. Degree is the highest exponent in the polynomial. So let m be the degree of the numerator. Let m be the degree of the denominator. Now for horizontal asymptote, there are three cases. Case 1. If m is greater than n, if the top degree is greater than the bottom degree, then there's no horizontal asymptote. If the top degree is larger than the bottom degree, then there's no horizontal asymptote. Case 2. If m is less than n, if the top degree is less than the bottom degree, then the horizontal asymptote is always y equal to 0. If the top degree is less than the bottom degree, then the horizontal asymptote is always y equal to 0, which is the x-axis. Case 3. If m equal to n, if the top and the bottom has the same degree, if the top and the bottom has the same degree, the horizontal asymptote is always y equal to b. The horizontal asymptote is always y equal to b, where b is the ratio of the leading coefficient in the numerator and the denominator. B is the ratio of the leading coefficient in the numerator and denominator. Next, based on these three rules, let's do some examples. Find the horizontal asymptote for each of the following rational functions. First function, f of x is x squared minus 4x plus 3 over 2x plus 5. We try to find the horizontal asymptote. So first step, we try to find the leading term on the top and the bottom, then compare their degrees. Leading term is a term of the highest power. So on the top, the leading term is x squared. Leading term is always a term of the highest power. That's degree 1, degree 2, degree 1, degree 0. Leading term on the bottom is x, is 2x. That's the term in the bottom has the highest power, which is 2x. Now, let's compare their degree. In the top, for the top polynomial, degree is 2. For the bottom polynomial, degree is 1. If the top degree is larger than the bottom degree, then there are no horizontal asymptote. If the top degree is larger than the bottom degree, then there are no horizontal asymptote. Here, the top degree is 2, bottom degree is 1. If the top degree is larger than the bottom degree, then there are no horizontal asymptote. Next example, g of x is 4x squared plus 5x minus 6 over x to the power 4 minus 16. So in order to find a horizontal asymptote, let's first of all find the leading term on the top and the bottom, and then compare their degrees. The leading term on the top is 4x squared. Leading term is a term of the highest power. So leading term on the top is 4x squared. Leading term on the bottom is x to the power of 4. Here, the degree of the top is 2, and the degree of the bottom is 4. Degree of the top is 2. Degree of the bottom is 4. If the top degree is less than the bottom degree, then the horizontal asymptote is always the line y equal to 0. If the top degree is less than the bottom degree, then the horizontal asymptote is always the line y equal to 0. So the horizontal asymptote is always the line y equal to 0. Next example, h of x is 2x squared plus 9x plus 10 over 4x squared minus 25. We try to find a horizontal asymptote. So first step, let's try to find their leading terms. For the numerator, the leading term here is 2s squared. For the denominator, the leading term here is 4s squared. Here, both top and bottom has degree 2. Both top and bottom has degree 2. If both the denominator and numerator have the same degree, if the top and the bottom has the same degree, if they have the same degree, the horizontal asymptote is always in the form of y equal to b, where b is the ratio of the leading coefficients. On the top, the leading coefficient is 2. On the bottom, the leading coefficient is 4. So, horizontal asymptote is y equal to 2 over 4. Horizontal asymptote is always the ratio of the leading coefficients in the top and the bottom, in the numerator and denominator. Here, leading coefficient of the numerator is 2. Leading coefficient of the denominator is 4. So, the horizontal asymptote is always y equal to b, where b is the ratio of the leading coefficient on the top and the bottom, which is 2 over 4. 2 over 4 can be reduced as 1 over 2. 2 over 4 can be reduced as 1 over 2. So that's the horizontal asymptote of this rational function h. Next, let me try to find vertical asymptotes. Here's the rule. Let f of x be a rational function in the form of f of x equal to p of x over q of x, where p of x and q of x, they are both polynomial functions. For all real number a, if q of a is 0, that means if I plug in a to the bottom, I get 0. If a makes the bottom 0, but if q of a is 0, but p of a is not 0, that means this number a here, this a makes the denominator 0, but the numerator is not 0, then we say s equal to a is a vertical asymptote. If there's a real number a, which makes the denominator 0, but the numerator not 0, then s equal to a is a vertical asymptote. Next, let's look at some examples. In the previous example, find the vertical asymptotes. First example, f of x is s squared minus 4x plus 3 over 2x plus 5. In order to find the vertical asymptote, I first of all set the denominator equal to 0. In order to find the vertical asymptote, I first of all set the denominator equal to 0. Find x. I first of all set the denominator equal to 0. Then solve the equation for x. I can first of all subtract 5 on both sides. Subtract 5 from both sides. I get 2s equal to negative 5. Next, I can divide both sides by 2. I get s equal to negative 5 over 2. Now, we know that x equal to negative 5 over 2, which will make the denominator 0. But we need to make sure this number doesn't make the top 0. If this number also makes the top 0, it doesn't count as a vertical asymptote. Let's check. If I plug in negative 2 over 5 into the numerator, what do we get? If I plug negative 5 over 2 into the numerator, what do we get? We have negative 5 over 2 squared minus 4 times 5 over 2 plus 3. I plug in negative 5 over 2 into the numerator. If this number doesn't make the numerator 0, then this is the vertical asymptote. Otherwise, it doesn't count. Let's check. Negative 5 over 2 squared is 25 over 4. Negative 4 times negative 5 over 2. If we multiply, that's 4 divided by 2 is 2. 2 times 5 is 10. Double negative is positive. I get positive 10 plus 3. Add the number first. 10 plus 3 is 13. 13 can be rewritten as 13 over 1. Then find the common denominator. For 4 and 1, the common denominator is 4. So in the second fraction, I can multiply top and bottom by 4. I get 25 over 4 plus 52 over 4, which is 77 over 4, which is not 0. So you can see that negative 5 over 2 make the bottom 0, but it doesn't make the top 0. So this is the vertical asymptote. So the vertical asymptote is s equal to negative 5 over 2. For function f, the vertical asymptote is negative 5 over 2. For function f, the vertical asymptote is s equal to negative 5 over 2. Now, how about function g? In order to find the vertical asymptote, we first of all set the denominator equal 0, solve for x, and then make sure if the solution doesn't make the top 0, then the solution is a vertical asymptote. So first of all, we set the denominator equal to 0. First of all, we set x to the power 4 minus 16 equal to 0. Then this polynomial can be factored as s squared plus 4 times s squared minus 4. Those are difference of perfect squares. A squared minus b squared is always a plus b times a minus b. We can treat x to the power 4 as x squared squared. 16 can be written as 4 squared. So x to the power 4 minus 16 can be factored as s squared plus 4 times s squared minus 4. S squared plus 4 cannot be factored any further. But s squared minus 4, that's also a difference of perfect squares. That can be factored as x plus 2 times s minus 2, set equal to 0. Then solve each equation individually. In the first equation, we have s squared plus 4 equal to 0. In the second equation, we have x plus 2 equal to 0. Then we have s minus 2 equal to 0. Solve each equation individually. In the first equation, I can subtract 4 from both sides. I get s squared equal to negative 4. If I take square root, I get plus or minus sign. We know that square root of negative 4 can be rewritten as square root of 4 times square root of negative 1. Square root of 4 is 2. Square root of negative 1 is I. So here s equal to plus or minus 2i. Solve the second equation, s equal to negative 2. Solve the third equation, s equal to 2. For asymptotes, for vertical asymptotes, we only consider real numbers. For vertical asymptote, we only consider real numbers. This is an imaginary number, it doesn't count. Plus minus 2i is an imaginary number, it doesn't count. So these two answers are rejected. What's left is s equal to negative 2 and positive 2. They may be the vertical asymptotes. Let's check. Let's plug in both numbers into the numerator. If I plug in negative 2 to the numerator, what do we get? Plug in negative 2 here. If I plug in negative 2, I get 4 times negative 2 squared plus 5 times negative 2 minus 6. Negative 2 squared is 4. 4 times 4 is 16. 5 times negative 2 is negative 10. 16 minus 10 minus 6 is 0. So if negative 2 also make the numerator 0, then it doesn't count. Negative 2 doesn't count. So this answer is also rejected. If negative 2 make the numerator 0, it doesn't count. Let's check positive 2. If I plug in positive 2 to the function, to the numerator, what do we get? I get 4 times 2 squared plus 5 times 2 minus 6. 2 squared is 4. plus 5 times 2 minus 6. 4 times 4 is 16. 5 times 2 is 10 minus 6. 16 plus 10 is 26. 26 take away 6 is 20. 20 is not 0. So if 20 is not 0, that means s equal to 2 is a vertical asymptote. So the vertical asymptote is s equal to 2. So for function g, the vertical asymptote is s equal to 2. Part C. Function h of x is 2s squared plus 9x plus 10 over 4s squared minus 25. We try to find the vertical asymptote. So first step, I set the numerator equal to 0. First step, I set the numerator equal to 0. Set 4s squared minus 25 equal to 0. Then we can try to factor this polynomial. This function can be factored as 2x plus 5 times 2x minus 5. Since they are difference of perfect squares, then set each of them equal to 0. Set both factors equal to 0. We get 2s plus 5 equal to 0 and 2s minus 5 equal to 0. Solve both equations individually. In the first equation, I can subtract 5 from both sides. I get 2s equal to negative 5. Then I can divide both sides by 2. I get s equal to negative 5 over 2. In the second equation, I can add 4 to both sides. I get 2s equal to 5. Then I can divide both sides by 2. I get s equal to 5 over 2. That's the solution from denominator. Next, let's check numerator. Plug in both answers into the numerator. Let's plug in negative 5 over 2 first. If I plug negative 5 over 2 into the numerator, the numerator is 2s squared plus 9x plus 10. I get 2 times negative 5 over 2 squared plus 9x plus 10. Negative 5 over 2 squared is 25 over 4 plus 9 times negative 5 over 2 plus 10. 2 can be rewritten as 2 over 1. Nine can be rewritten as 9 over 1. 10 can be rewritten as 10 over 1. Then here, 4 and 2 can be reduced. It can be reduced. For 2 and 4, I can divide both numbers by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. So I get 25 over 2. For the second term here, 9 times negative 5 is negative 45. 1 times 2 is 2 plus 10 over 1. 25 over 2 minus 45 over 2. They have the same denominator. So do the first two terms first. 25 minus 45 is negative 20. I get negative 20 over 2 plus 10 over 1. Negative 20 over 2 is 10 over 1. Negative 10 over is negative 10. Negative 10 plus 10 is 0. Since negative 5 over 2 make the numerator 0, this is not a vertical asymptote. This is rejected. Since negative 2 over 5, negative 5 over 2 make the numerator 0, this is rejected. It cannot be the vertical asymptote. How about 5 over 2? Do the same thing. We plug 5 over 2 into the numerator. Plug 5 over 2 into the numerator. We get 2 times 5 over 2 squared plus 9 times 5 over 2 plus 10. 5 over 2 squared is 25 over 4 plus 9 times 5 over 2 plus 10. 2 can be rewritten as 2 over 1. 9 can be rewritten as 9 over 1. Then simplify. 2 and 4 can be reduced. I can divide both numbers by 2. If I divide both numbers by 2, 2 divided by 2 is 1, 4 divided by 2 is 2. So first term can be rewritten as 25 over 2. For the second term, we can multiply 3 across. 9 times 5 is 45. 1 times 2 is 2, plus 10. Now, for the first two terms, 25 over 2 plus 45 over 2, they have the same denominator. We keep denominator and the numerator. 25 plus 45 is 70. 70 over 2 is 35. 35 plus 10 is 45, which is not 0. If I plug in 5 over 2 to the numerator, I don't get 0. That means this is the vertical asymptote. So the vertical asymptote is S equal to 5 over 2. That's the vertical asymptote of this rational function. So that's the horizontal asymptote. That's the vertical asymptote. So that's how we find the horizontal and vertical asymptotes. Next, let me show you how to graph rational functions. Graph each of the following rational functions, indicating the X and Y intercepts, horizontal and vertical asymptotes, and the end behaviors. First example, f of x is x minus 3 times s plus 5 over s minus 1. In order to graph this function, let's find the horizontal and vertical asymptotes first. For horizontal asymptote, let's compare the degree on the top and the bottom. First of all, let's find the leading term. In order to find the leading term on the top, we have to multiply everything out, but it may be too much work. A shortcut to find the leading term is that we multiply leading term on each factor. A shortcut to find leading term is that we multiply leading term on each factor. For the first factor, leading term is x. For the second factor, leading term is also x. So for the leading term, I multiply leading term on each factor. I get s squared. That's your shortcut to find leading term. That's your shortcut to find leading term on the top. On the bottom, we can see that the leading term here is x. Leading term is the term with the highest power. So leading term on the top is s squared. Leading term on the bottom is x. Since the top has higher degree than the bottom, this top degree is larger than the bottom degree, horizontal asymptote does not exist. If the top degree is more than the bottom degree, then there's no horizontal asymptote. So there are no horizontal asymptote. How about the vertical asymptote? For vertical asymptote, we set the denominator equal to 0. Solve the equation for x. We get s equal to 1. Then plug in 1 to the numerator. Make sure the numerator is not 0. If I plug 1 to the numerator, 1 minus 3 is negative 2. 1 plus 5 is 6. Negative 2 times 6 is not 0. So this is the vertical asymptote. So in this function, there are no horizontal asymptote. The vertical asymptote is s equal to 1. That's the first step. Find the horizontal and vertical asymptotes. Next, find the zeros. Find the zeros of this function. In order to find the zero, we set the numerator of this rational function to 0. When the numerator of a fraction is 0, the fraction itself is 0. So for the zeros, we set the numerator of the rational function to 0. When the numerator is 0, the entire function is 0. So I set the numerator to 0. Set the numerator to 0. Solve the equation for x. We get x minus 3 equal to 0. X plus 5 equal to 0. S equal to 3. S equal to negative 5. For rational function, we don't care about the multiplicity of the zeros. For rational functions, we don't care about the multiplicity of the zeros. we try to find a 0. We don't care about number multiplicity. So there are 2 zeros. S equal to 3, S equal to -5. Next, let's make number line test. Put a vertical asymptote and the zeros on the number line. Put the numbers in order. The smallest is -5. Next is 1. Largest is 3. Put the zeros and the vertical asymptotes on the number line. Then if I cut the line 3 times, I make it into 4 regions. Here, -5 is a 0. 1 is a vertical asymptote. 3 is a 0. If I cut a line 3 times, I cut into 4 regions. Let's use number line test. Pick test number first. I can first of all pick test number less than -5. I pick -6. Pick test number between -5 and 1. Make it easier, let me pick 0. Pick test number between 1 and 3. We can pick 2. Then pick test number more than 3. I can pick 4. Plug each test number into function f. Next, we plug each test number into function f. If I plug in -6, on the numerator, -6 minus 3 is negative. -6 plus 5 is -1, which is also negative. On the denominator, -6 minus 1 is -7, which is negative. Then if we multiply, on the numerator, double negative is positive. Positive number divided by negative number is negative. So, if there are odd number of negative sign, when we multiply or divide, answer is negative. If there are even number of negative sign, when we multiply or divide, answer is always positive. Now I plug in 0. If I plug in 0, 0 minus 3 is negative. If I plug in 0 here, 0 plus 5 is 5. It's positive. If I plug in 0 here, 0 minus 1 is -1, which is negative. Then multiply or divide. On the numerator, negative number times positive number is negative. And then negative number divided by negative number is positive. So in general, if there are even number of negative sign, when we multiply or divide, answer is positive. Next, let's plug in 2. If I plug in 2 into function f, 2 minus 3 is negative. 2 plus 5 is 7, which is positive. On the bottom, 2 minus 1 is 1, which is positive. Then multiply or divide. On the numerator, negative number times positive number is negative. And then negative number divided by positive number is negative. If there are odd number of negative sign, when we multiply or divide, answer is always negative. Next, plug in 4. 4 minus 3 is positive. 4 plus 5 is positive. On the bottom, 4 minus 1 is also positive. Positive number times positive number is positive, and then positive number divided by positive number is positive. Next, let's sketch a graph. When we sketch a graph, first step, draw the asymptotes and the zeros. First step, draw the asymptotes and the zeros. There are no horizontal asymptote. There's a vertical asymptote at s equal to 1. There are 2 zeros, 3 and -5. There are 2 zeros, 3 and -5. One, 2, 3, 4, 5. There are 2 zeros, 3 and -5. Then let's sketch a graph. When x is less than -5, function f is negative. When x is less than -5, function f is negative. If function f is negative, that means it goes below the x-axis. It goes below the x-axis. When function f is negative, it goes below the x-axis. Now, between -5 and 1, function f is positive. Between -5 and 1, function f is positive. It's positive means it goes above x-axis. Here, 1 is a vertical asymptote. The curve must eventually get very, very close to the asymptote. The curve must eventually get very, very close to the asymptote. And we know that rational function is a smooth curve. The graph of rational function is a smooth curve. It's not smooth here. We try to make it smooth. Try to fix the curve, make it smooth. Try to fix the graph, make it smooth. The graph of rational function is smooth. It's a smooth curve. Next, between 1 and 3, when x is between 1 and 3, f of x is negative. Negative means it goes below the x-axis. So between 1 and 3, the curve goes below x-axis. This is asymptote. The graph must get close to the asymptote, but don't touch the asymptote. Then, when x is greater than 3, function f is positive. If it's positive, it means it goes above x-axis. So that's the graph of function f. That's the graph of the function f. That's the X-intercepts. And for the Y-intercept, for X-intercept, that's the zeros. X-intercept is the zeros. We have 3, 0 and -5, 0. X-intercept is the same as the zeros. For the Y-intercept, we plug in 0 for x. For the Y-intercept, plug in 0 for x. Y equal to f of 0, which is 0 minus 3 times 0 plus 5 over 0 minus 1. On the numerator, we get -3 times 5. Denominator is -1. So -3 times 5 is -15. -15 divided by -1 is +15. So the Y-intercept is 0, 15. Y-intercept is 0, 15. Which means this point here is 15. That's the Y-intercept. This point here in the Y-axis is 15. That's the Y-intercept. So, horizontal asymptote, we see that it does not exist. There's no horizontal asymptote. For vertical asymptote, here we find 1, which is s equal to 1. That's one vertical asymptote, s equal to 1. Next, for the end behavior, we have 4 ends here. That's one end here. That's another end behavior. That's another end behavior. We have 4 end behavior here. We have 4 end behavior. We have 4 end behavior in this graph. So, as x approaches to infinity, x approaches to infinity, if x goes all the way to the left, the f of x goes all the way up. If x goes to the left, function f goes all the way up. So as x approaches infinity, f of x approaches to infinity. As x approaches infinity, function f goes all the way up, which means it goes to infinity. As x approaches to negative infinity, as x approaches to negative infinity, as x approach all the way to the left, function f goes all the way down. So function f approaches to negative infinity. As x approaches to negative infinity, f of x approaches to negative infinity. Now, here, for this end behavior here, we can see that as x approaches to 1, as x approaches to 1 from left side, as x approaches to 1, as x approaches 1 from left, this is left side. As x approaches 1 from left, function f go all the way up to infinity. As x approaches 1, as x approaches 1 from left, as x approaches 1 from the left, f of x goes all the way up, which means it goes to infinity. As x approaches 1 from left, f of x approaches infinity. And for this end behavior here, let's x approach to 1 from the right. As x approaches to 1 from the right, f of x goes all the way down, which means it approaches to negative infinity. As x approaches to 1 from the right, f of x approaches to negative infinity, goes all the way down. So f of x approaches to negative infinity. Note on the end behavior of this graph. So we have 4 end behavior here. 1, 2, 3, 4. This end behavior occurs when x approaches to negative infinity. This end behavior occurs when x approaches to infinity. That's the end behavior when x approaches to 1 from left side. That's the end behavior when x approaches to 1 from the right side. We have 4 end behavior here. Those are the end behaviors of function f. Next example, f of x is 2x plus 7 times x minus 3 over x plus 1 squared. We try to graph this rational function. So let's find the horizontal and vertical asymptotes first. For horizontal asymptote, we need to find the leading term on the top and the bottom. In general, in order to find the leading term, we need to multiply the polynomial out. But there's a shortcut. There's a shortcut for the leading term. For leading term, we can take leading term from each factor and then multiply out. Leading term in the first factor is 2x. And leading term in the second factor is x. 2x times x is 2x squared. That's the leading term of the numerator. If we multiply the numerator out, this is the leading term. And for the denominator, do the same thing. Instead of multiply everything out, a shortcut is take a leading term from this factor. We get x squared, which is x squared. Then let's compare their degree. The degree in the numerator is 2. Degree in the denominator is also 2. If the denominator and numerator have the same degree, if top and bottom have the same degree, then for horizontal asymptote, we let y equal to the ratio of the leading coefficient on the top and the bottom. Leading coefficient of the top is 2. Leading coefficient of the bottom is 1. 2 over 1 is 2. So the horizontal asymptote is y equal to 2. If the degree on the top and the bottom is the same, the horizontal asymptote is y equal to the ratio of the leading coefficient on the top and the bottom. Here, leading coefficient of the top is 2. Leading coefficient of the bottom is 1. 2 over 1 is 2. So the horizontal asymptote is y equal to 2. For vertical asymptote, we first of all set the denominator equal to 0. Then solve the equation for x. In this equation, I can first of all take square root on both sides. I get s plus 1 equal to 0. Then subtract 1 from both sides. S equal to -1. Next, plug -1 into the numerator. Make sure it doesn't make the numerator 0. If this solution doesn't make the numerator 0, then this is the vertical asymptote. Let's plug -1 into the numerator. 2 times -1 is -2. -2 plus 7 is 5. If I plug -1 here, -1 minus 3 is -4. 5 times -4 is -20, which is not 0. If this solution doesn't make numerator 0, then this is the vertical asymptote. So that's the asymptotes. Next, let's find the zeros of this rational function. In order to find a zero for rational function, we set the numerator equal to 0. In a fraction, when the numerator is 0, the entire fraction is 0. So I set the numerator equal to 0. Then solve the equation for x. Set the numerator equal to 0. Solve the equation for x. I get 2x plus 7 equal to 0. X minus 3 equal to 0. Solve both equations individually. In the first equation, I can subtract 7 from both sides. I get 2s equal to -7. Then I divide both sides by 2. S equal to -7 over 2. In the second equation, I can add 3 to both sides. I get s equal to 3. So those are the zeros of this function f. Next, let's make a number line test using the vertical asymptote and the zeros of the rational function. Make number line test using the vertical asymptote and the zeros of the rational function. Write this number in orders. The smallest is -7 over 2. 7 over 2 is about 3.5. If you take 7 divided by 2, it's about 3.5. So that's the smallest. Next is -1. And 3 is the largest. Put the zeros and the asymptotes and vertical asymptotes in order. We will take care of horizontal asymptote later. Now for number line test, only use the vertical asymptote and the zeros. We will take care of the horizontal asymptote later. Now, 3 number divide the line into 4 regions. 3 number divide the line into 4 regions. This is a 0. -1 is a vertical asymptote. 3 is another 0. Now, 3 number divide line to 4 regions. Let's pick some test numbers on each region. Let's pick some test numbers on each region. In the first region, pick test number less than -7 over 2. 7 over 2 is 3.5. Pick test number less than -3.5. We can pick -4. Next, pick test number between -3.5 and -1. We can pick -2. Next, pick test number between -1 and 3. We can pick 0. Next, pick test number greater than 3. I can pick 4. Next, plug each test number into function f. Plug each test number into function f. Let's plug in -4 first. If I plug in -4, 2 times -4 is -8. -8 plus 7 is -1. If I plug in negative 4 here, negative 4 minus 3 is negative 7, which is negative. If I plug negative 4 into the denominator, negative 4 plus 1 is negative 3. Negative 3 squared is positive 9. So denominator is positive. Then multiply. Double on the numerator, double negative is positive. Positive number over positive number is positive. If there are even number of negative sign, when we multiply or divide, the answer is always positive. If there are odd number of negative sign, when we multiply or divide, the answer is negative. Next, let's plug in negative 2. If I plug in negative 2, 2 times negative 2 is negative 4. Negative 4 plus 7 is positive 3. So it's positive. If I plug negative 2 here, negative 2 minus 3 is negative 5, which is negative. Next, plug negative 2 into the denominator. Negative 2 plus 1 is negative 1. Negative 1 squared is positive 1. So denominator is positive. Then multiply. In the numerator, positive number times negative number is negative. And then negative number divided by positive number is negative. If there are odd number of negative sign, when we multiply or divide, the answer is always negative. Next, plug in 0. If we plug in 0 here, 2 times 0 is 0. 0 plus 7 is positive. If I plug in 0 here, 0 minus 3 is negative 3, which is negative. If I plug 0 to the denominator, 0 plus 1 is 1. 1 squared is 1, which is positive. Then multiply. If there are odd number of negative sign, the product is, when we multiply or divide, the answer is negative. Next, plug in 4. 2 times 4 is 8. 8 plus 7 is positive 15. That's positive. Plug in 4 here. 4 minus 3 is 1. 1 is positive. Next, plug in 4 into the denominator. 4 plus 1 is 5. 5 squared is 25, which is positive. That's the sign of function f. Next, sketch a graph based on this information here. First step, draw the asymptotes and the zeros first. First step, draw the asymptotes and the zeros first. Horizontal asymptote is y equal to 2. Horizontal asymptote is y equal to 2. We draw dashed line for asymptotes. This is a horizontal asymptote. Vertical asymptote is s equal to negative 1. Vertical asymptote is s equal to negative 1. The zeros are negative 7 over 2 and positive 3. Positive 3 is here. 1, 2, 3. That's positive 3. That's a 0. Negative 7 over 2. Negative 7 over 2 is the same as negative 3.5. Negative 2, negative 3, negative 4. 3.5 is somewhere in between negative 3 and negative 4. That's negative 7 over 2. Negative 7 over 2 is negative 3.5, which is the middle of negative 3 and negative 4. Next, let's sketch a graph. When x is less than negative 7 over 2, function f is positive. when x is less than -7/2, function f is positive, which means the curve go above x-axis. The curve go above x-axis. Now, if there is horizontal asymptote, the curve will get close to the asymptote. The curve will eventually get close to the asymptote. Now, there are two ways to get close to asymptote. There are two ways to get close to the asymptote. It may get close to the asymptote like this, from below. The curve may get close to the asymptote from below. That's one possibility. The curve may get close to the horizontal asymptote from below. Another possibility is that the curve may go through the curve. The curve may go through the asymptote first, then get close to the asymptote from above. There are two possibilities. The curve may get close to the asymptote in two ways. It may get close to the asymptote from below, or it may go through the asymptote first, then get close to the asymptote from above. There are two possibilities. We need to verify this. So we must test for the asymptote. We need to do a test for the asymptotes on the left side and right side. We must test for the horizontal asymptotes from left side and right side. So there's one more test. If the graph has a horizontal asymptote, there's one more test. If the graph has a horizontal asymptote, there's one more test. We plug in some large negative number and plug in some large positive number. We plug in -100 and 100. We test some large negative number and some large positive number. Plug -100 into function f. Here, in order to save time, I use calculator. Plug in -100 into function f for x. We do 2 times 100 plus 7 times 100 minus 3 over 100 plus 1 squared. Here, in order to save time, I use calculator. It's almost impossible to do this by hand, so here I use calculator. I plug -100 into the function f. 2 times -100 plus 7 times -100 minus 3 over -100 plus 1 squared. Use calculator. I get 2.028. Use calculator, I get 2.028. Next, for f of 100, we plug 100 into function f. I do 2 times 100 plus 7 times 100 minus 3 over 100 plus 1 squared. Plug in some large number. We can use either 100 or 1000, doesn't matter. Plug in some large number. If I plug in 100, I use my calculator. I get 1.968. Now, f of -100 is positive 2.028. This line is 2. Horizontal asymptote is 2. So if I plug in -100, I get 2.028. Means the curve will eventually go above the horizontal asymptote. That means the curve will eventually go above horizontal asymptote. That means the curve will go through the asymptote first, then approach the curve, approach the asymptote from above. Because f of -100 is 2.028, that means the curve will eventually go through the asymptote, then approach the asymptote from above. For rational function, asymptote has two possibilities. The curve may approach the asymptote from below, or the curve may go through the asymptote first, then approach it from above. There are two possibilities. Here, since when I plug in -100, when I plug in very large negative number, I get 2.028, which is above 2. That means the curve will eventually go through the asymptote, then approach from above. Now, next, when x is between -7/2 and -1, when x is between -7/2 and -1, function f is negative, which means function f is below x-axis, and function f must get close to the asymptote. function f must get close to the asymptote. And we know that rational function must be very smooth. The curve must be very, very smooth. So let's fix this point here, make the curve smooth. Keep the same shape, but make the curve smooth. Keep the same shape, but make the curve smooth. Next region. When s is between -1 and 3, function f is negative. When s is between -1 and 3, function f is negative. That means the curve is below x-axis. So from -1 to 3, the curve is below x-axis. The curve must get close to the asymptote. It's below x-axis, and it must get close to the asymptote. Next, when s is more than 3, function f is positive. Let me see, go above x-axis. Again, there are two possibilities. The curve may approach the asymptote from below. That's one possibility. Or it may go through the curve first, then approach from above. There are two possibilities. So here, let's plug in some large number into function f. If I plug in some large number, if I plug in 100, function f is about 1.968, which is below 2. This number is below 2, which means the curve approaching the asymptote from below. It won't go above. It approaches the asymptote from below. That's the rough graph of function f. That's a rough sketch of function f. Next, let's find the horizon. Let's find x and y intercepts. There are two x-intercepts. X-intercept is the same as 0. We have -7/2 and 3. X-intercept is the same as 0. We have -7/2 and 3, which is -7/2, 0 and 3, 0. That's an x-intercept. For the y-intercept, we plug 0 into function f. For the y-intercept, plug 0 into function f. If we plug in 0, we have 2 times 0 plus 7 times 0 minus 3 over 0 plus 1 square. Then on the numerator, 2 times 0 is 0. 0 plus 7 is 7. 0 minus 3 is -3. On the denominator, 0 plus 1 is 1. 1 squared is 1. Then multiply. 7 times -3 is -21. -21 divided by 1 is -21. So the y-intercept is 0, -21. The y-intercept is 0, -21, which is here. We didn't draw the y-intercept. We didn't draw the y-axis in scale. So let's mark this point, -21. That's the y-intercept, -21. And we know that the horizontal asymptote is y equal to 2. Vertical asymptote is s equal to -1. Vertical asymptote is s equal to -1. That's the vertical asymptote. That's the horizontal asymptote. And for the end behavior, here we can see that there are 4 end behaviors. For the end behavior, we have to say 4 things. There are 4 end behaviors in this graph. For the end behavior, as x approach to infinity, as x approaches to infinity, as s goes all the way to the right, function f gets very close to 2 from below. So f of x approach to 2 from below. Put a little minus here. This means s approach to 2, but it's a little less than 2. S will get very close to 2, but it's a little less than 2. This little minus sign here means f of x is approach to 2, but it's a little below 2. It's very close to 2, but it's a little less than 2. It will be very close to 2, but it's a little less than 2. So f of x approach to 2, but it's very close. It's a little less than 2. As s approach to negative infinity, as s approach to negative infinity, as the curve, as x go all the way to the left, the curve gets very close to 2. As the curve gets, as x go all the way to the left, the curve gets very close to 2 from above. This curve is above 2. So function f approach to 2 from above. This little plus means it's a little above 2, a little more than 2. This little minus means a little less than 2. So as s approach to negative infinity, as s goes all the way to the left, function f gets very close to 2 from above. As s gets very close to infinity, as s approaches infinity, function f gets very close to 2 from below. We can find it from these two values here. When I plot in very large negative number, f of x is a little above 2. When we plot in very large number, very large positive number, f of x is a little below 2. So as s approaches to infinity, approaches to large number, f of x approaches to 2 from left side. As s approaches to 2, as x approaches to infinity, f of x approaches to 2 from the right side. Next, for another end behavior here, when x approaches to -1 from left side, f of x goes all the way down, which is negative infinity. As x approaches to -1 from left, f of x approach to negative infinity. As x approaches to -1 from left, f of x approach to negative infinity. As x approaches to -1 from the right, from the right side, as x approaches to -1 from the right side, f of x also approaches to negative infinity. It goes all the way down. So as x approaches to -1 from the right, f of x approaches to negative infinity. That's the end behavior of this graph. Next example, f of x is x minus 2 over x plus 2 squared times x minus 6. We try to graph this rational function. So first step, let's find the horizontal and vertical asymptotes first. For horizontal asymptote, let's find the leading term on the top and the bottom first. On the numerator, the leading term is x. That's very clear. In the denominator, in order to find the leading term, we have to multiply out. But there's a shortcut. We can take a leading term from each factor. A shortcut is we can take a leading term from each factor and then multiply out. In the first factor, leading term is x, so we have x squared. In the second factor, leading term is also x, so we get s squared times x, which is s cubed. If we multiply the denominator out completely, the leading term is s cubed. Next, compare their degree. Degree on the top is 1. Degree on the bottom is 3. If the top degree is less than the bottom degree, then the horizontal asymptote is always y equal to 0. If the top degree is less than the bottom degree, then the horizontal asymptote is always y equal to 0. For vertical asymptote, we set the denominator equal to 0. For the vertical asymptote, we set the denominator equal to 0. Then solve the equation for x. Here we have x plus 2 squared equal to 0, and x minus 6 equal to 0. Solve each equation individually. For the first equation, I can take square root on both sides. So I have x plus 2 equal to 0. Then subtract 2 from both sides. I get s equal to -2. In the second equation, I get s6 to both sides. I get s equal to 6. Now I need to verify. If I plug in this solution into the numerator, I make it 0, then this solution doesn't count as a vertical asymptote. But if this solution doesn't make the numerator 0, then it counts as vertical asymptote. If I plug in -2, -2 minus 2 is -4, which is not 0. So this counts as a vertical asymptote. If I plug in 6, in the numerator, 6 minus 2 is 4, which is also not 0. So they are both vertical asymptote. In this problem, we have 2 vertical asymptotes. They are both vertical asymptotes. That's an asymptote. That's an asymptote of this polynomial, of this rational function. Next, let's find the zeros. In order to find the zeros of a rational function, we set the numerator equal to 0. So for the zeros, we set the numerator equal to 0. Then solve the equation for x. I get s equal to 2. That's the zero. That's the zero of this rational function. That's the zero of the rational function. Next, let's make a number line test. Let's make a number line test using the vertical asymptotes and the zeros. Make a number line test using the vertical asymptotes and the zeros. Put the numbers in order. The smallest is -2. Next is 2. 6 is the largest. 3 number divide the line to 4 regions. Here, -2 is a vertical asymptote. +2 is a 0. +6 is a vertical asymptote. We will take care of the horizontal asymptote later. For now, let's use number line test. Let's use number line test by using the vertical asymptote and the zeros. We will take care of the horizontal asymptote later. Now, 3 number divide the line to 4 regions. For each region, let's pick test number. Pick test number less than -2. We can pick -3. Pick test number between -2 and 2, we get 0. Pick test number between 2 and 6, we get 4. It can be any number between 2 and 6. And pick test number more than 6, we can use 7. Next, plug in each test number into function f to test for positive or negative sign. If I plug in -3 on the numerator, -3 minus 2 is -5, which is negative. If I plug 3 into the denominator, -3 plus 2 is -1. -1 squared is +1. It's positive. If I plug -3 into here, -3 minus 6 is -9, which is negative. Then let's multiply and divide. In the denominator, positive number times negative number is negative, and negative number divided by negative number is positive. In general, if there are even number of negative sign, then when we multiply or divide, answer is always positive. If there are odd number of negative signs, then when we multiply or divide, answer is always negative. Next, plug in 0. If I plug in 0, and then in the numerator, 0 minus 2 is negative. If I plug in 0 to the denominator, 0 plus 2 is 2. 2 squared is 4, which is positive. If I plug in 0 here, 0 minus 6 is negative 6, which is negative. Then let's multiply and divide. If there are even number of negative sign, when we multiply or divide, answer is always positive. Next, plug in 4. If I plug in 4 to the numerator, 4 minus 2 is positive 2, which is positive. If I plug 4 to the denominator, 4 plus 2 is 6. 6 squared is positive. If I plug 4 here, 4 minus 6 is negative 2, which is negative. Then let's multiply or divide. In the denominator, positive number times negative number is negative, and positive number divided by negative number is negative. If there are odd number of negative sign, when we multiply or divide, answer is always negative. Next, plug in 7. If I plug in 7 to the numerator, 7 minus 2 is 5, which is positive. If I plug 7 to the denominator, 7 plus 2 is 9. 9 squared is 81, which is positive. 7 minus 6 is 1, which is positive. Then let's multiply or divide. In the denominator, positive number times positive number is positive, and positive number divided by positive number is positive. Also, since there's a horizontal asymptote, let's also test for horizontal asymptote and the left end and right end. Let's also test for the horizontal asymptote. So we plug in some very large negative number and some very large positive number. Usually we use 100. If you use 1,000 or 10,000, doesn't matter. Let me use 100 here. If I plug negative 100 into function f, I get negative 100 minus 2 over negative 100 plus 2 squared times negative 100 minus 6. Here I use calculator. It's impossible to do 100 by hand manually. So let's use calculator. Plug in 100 for each x. Then use calculator. Here, when I plug in negative 100, use calculator, I get 0.0001 in my calculator. Next, let's plug in some very, very large positive number. If I plug in positive 100, I get 100 minus 2 over 100 plus 2 squared times 100 minus 6. Use my calculator, I get 0.0001. Both numbers are a little above 0. So that means at the left end and right end, the curve will approach the asymptote. The curve will approach the horizontal asymptote from above. That means at both ends, since both numbers are greater than 0. That means at both ends, in the left end and right end, the curve will approach the horizontal asymptote from above, since they are both above 0. Next, let's sketch a graph using this information here. Let's draw the asymptotes and the zeros first. Horizontal asymptote is y equals 0, which is an x-axis. That's in the horizontal asymptote. There are two vertical asymptotes, s equal to negative 2 and s equal to positive 6. Negative 1, negative 2. 1, 2, 3, 4, 5, 6. Those are the vertical asymptotes. Usually use dashed line to represent the vertical asymptotes. usually use dashed line to represent the vertical asymptotes. Next, let's plot zeros. 0 is s equal to 2. The 0 is also an S-intercept. So let's S-intercept at 2. Next, let's sketch a graph. When x is less than -2, function f is positive. When x is less than -2, function f is positive. So when x is less than -2, function f is positive. That's an asymptote. That's also asymptote. The curve must get close to both asymptotes. The curve must get close to both asymptotes, and it's above 0. It's above 0. So the only possibility is that the curve looks like this. And we know that when at the left end, when we plug in very large negative number, function f is above 0. So the function f is above the horizontal asymptote. The curve approaching the horizontal asymptote from above. The curve approaching the horizontal asymptote from above. That's the first piece. When x is less than -2. Now, when x is between -2 and 2, function f is positive. When x is between -2 and 2, function f is positive. That means function f, the curve is above the s-axis. So 2 is here. When x is between -2 and 2, the curve is above s-axis. And the curve must get close to the asymptote. The curve must get close to the horizontal, must get close to the vertical asymptote. When s is between 2 and 6, when s is between 2 and 6, f of x is negative. That means the curve is below s-axis. So between 2 and 6, the curve is below the s-axis. And the curve must get close to the asymptote. The curve must eventually get close to the vertical asymptote. Last piece. When s is more than 6, function f is positive, which means function f is above s-axis. So function f is above s-axis, and it must get closer to both asymptotes. The only possibility is that it looks like this. And also here, when we plug in very large number into function f, the value is above 0. That means the asymptote will approach to 0. The asymptote will get close to 0 from above. The curve will get close to the horizontal asymptote from above. The curve will get close to the horizontal asymptote from above. So that's a rough sketch for the function y equal to f of x. Next, let's find the asymptotes. Let's find the intercepts and the asymptotes. For an S-intercept, S-intercept is the zeros, which is 2, 0. That's an S-intercept, which is here. For the Y-intercept, we plug 0 into function f. For the Y-intercept, we plug 0 into function f. We get 0 minus 2 over 0 plus 2 squared times 0 minus 6, which is 0 minus 2 is -2 on the top. On the bottom, 2 squared is 4 times -6. That's -2 over -24. If we simplify, that's 1 over 12. Double negative is positive. So the y-intercept is 0, 1 over 12. That's the y-intercept. Since we didn't draw the y-axis in scale, so let's label this number to be 1 over 12. We didn't draw the y-axis in scale. We didn't draw the y-axis in scale, so let's label this number to be 1 over 12. And for horizontal asymptote, that's y equal to 0. For the vertical asymptote, we have s equal to -2 and s equal to 6. Next, for the end behavior, we have 1, 2, 3, 4, 5, 6. There are 6 end behaviors here. As x approach to infinity, as x approach to infinity, when we plug in very large number into function f, we can see that we get a number a little above 0. So as x approach to infinity, function f approach to 0 from above. As s approach to infinity, function f approach to 0 from above. Here, when we plug in very large number, function f is a little above 0. As s approach to negative infinity, as x approach to negative infinity, as s approach to negative infinity, function f approach to 0 from above. It's a little above 0. So f of x approach to 0 from above. When we plug in very large negative number, function f is a little above 0. So f of x approach to 0 from above. This little plus sign here means a little above 0. Little minus sign means a little below. Little plus sign here means a little above. Now, let's look at end behavior at -2. Let's look at the end behavior at -2. As x approach to -2 from left side, as x approach to -2 from the left, as x approach to -2 from the left, function f approach to infinity. Function f goes all the way up. As x approach to -2 from the left, function f go all the way up. So f of x approach to infinity. As x approach to -2 from the right, as x approach to -2 from the right, function f also go up to infinity. Next, let's look at the end behavior at 6. As x approach to 6 from the left side, function f go down to negative infinity. As x approach to 6 from left side, f of x approach to negative infinity. As x approach to 6 from left side, function f approaches to negative infinity. And on the other side, as s approaches to 6 from the right side, function f approaches to positive infinity. As x approaches to 6 from the right, f of x approaches to positive infinity. That's the end behavior of this graph. Next example, f of x is 4x plus 5 squared times x minus 4 over 2x minus 3 squared times x plus 4. We want to graph this rational function. So first step, let's find the horizontal and the vertical asymptotes. For horizontal asymptotes, let's find the leading term for the numerator and denominator first. For the numerator, in order to find the leading term, an easier way is take leading term on each factor and then multiply. Leading term for 4x plus 5 is 4x, and keep square outside. Leading term for x minus 4 is x. Then multiply. 4 squared is 16. S squared times x is x to the power of 3. That's the leading term of the numerator. Then for the denominator, let's find the leading term. An easier way is take a leading term from each factor and then multiply out. For 2x minus 3, the leading term is 2x. Keep square. And for x plus 4, leading term is x. Then multiply. 2 squared is 4. S squared times x is s cubed. That's the leading term of the denominator. Next, let's compare their degree. The degree of 16x cubed is 3. Degree of 4x cubed is also 3. If the top degree and the bottom degree are exactly the same, then for the horizontal asymptote, is y equal to the ratio of the leading coefficient. So here, since the degree on the top and the bottom is exactly the same, the horizontal asymptote is y equal to the ratio of the leading coefficients. Leading coefficient of 16x cubed is 16. Leading coefficient of 4x cubed is 4. So we take 16 over 4, which is 4. That means horizontal asymptote is y equal to 4. That's the horizontal asymptote. Next, for the vertical asymptote, we set the denominator equal to 0. We have 2x minus 3 squared times s plus 4 equal to 0. Then solve the equation for x. We first of all set each factor equal to 0. 2x minus 3 squared equal to 0. X plus 4 equal to 0. In the first equation, I can take square root on both sides. I get 2x minus 3 equal to 0. Then add 3 to both sides. We get 2x equal to 3. Then divide both sides by 2. S equal to 3 over 2. In the second equation, I can subtract 4 from both sides. I get s equal to negative 4. Next, plug each number into the numerator. If this number doesn't make the numerator 0, then this is a vertical asymptote. Let's plug in. If we plug 3 over 2 to the numerator, 4 times 3 over 2 is 6. 6 plus 5 is 11. 11 squared is 121. If I plug 3 over 2 here, 3 over 2 minus 4 is negative 5 over 2. 112 times 5 over 2 is not 0. So this is a vertical asymptote. Plug in negative 4. If I plug in negative 4 to the numerator, 4 times negative 4 is negative 16. Negative 16 plus 4 is negative 11. Negative 11 squared is 121. If I plug in negative 4 here, negative 4 minus 4 is negative 8. 121 times negative 8 is not 0. So they are both vertical asymptotes. They are both vertical asymptotes. When I plug in both numbers, the numerator is not 0. So they are both the vertical asymptotes. Next, let's find the 0 of this rational function. For zeros, we set only the numerator equal to 0, because for any fraction, if the numerator is 0, the fraction itself is 0. So for zeros, set the numerator equal to 0, only the numerator. For zeros, set the numerator equal to 0. We have 4x plus 5 squared times s minus 4 equal to 0. Then solve this equation for x. I can first of all separate it. What is 4x plus 5 squared equal to 0? X minus 4 equal to 0. Solve each equation individually. In the first equation, I can take square root on both sides. I get 4x plus 5 equal to 0. Subtract 5 from both sides. We get 4x equal to negative 5. Then divide both sides by 4. S equal to negative 5 over 4. That's a 0. Solve the other equation. I can add 4 to both sides. I get s equal to 4. That's another 0. So you got 2 zeros here. Next, make number line test using the zeros and the vertical asymptote. Next, make number line test using the zeros and the vertical asymptote. Use the number line to test the function f for positive negative signs. Put these numbers on the number line. Put in order from smallest to largest. The smallest is x equal to negative 4. Then next one is negative 5 over 4. 5 over 4 is about 1.25, so that's negative 1.25. Next is 3.3 over 2. 3 over 2 is about 1.5. 3 over 2 is about 1.5, 1.5, 1.5. And the largest is 4, it's positive 4. 4 points cut a line to 5 different regions. Four points cut a line to 5 different regions. So here, negative 4 is a vertical asymptote. Negative 5 over 4 is a 0. 3 over 2 is a vertical asymptote. And number 4 is a 0. Next, let's pick some test number on each region. Pick number less than negative 4. I can pick negative 5. Pick number between negative 4 and negative 5 over 4. Negative 5 over 4 is about negative 1.25. So pick number between negative 4 and negative 1.25. I can pick negative 2. Pick number between negative 1.25 and 3 over 2. 3 over 2 is about 1.5. Pick number between negative 1.25 and positive 1.5. I can pick 0. Next, pick number between 1.5 and 4. I can pick 2. Next, pick number greater than 4. I can pick 5. Then, plug each test number into function f. We try to test for positive negative sign in function f. If I plug in negative 5, 4 times negative 5 is negative 20. Negative 20 plus 5 is negative 15. Negative 15 squared is positive. Double negative is positive. Next, plug in negative 5 here. Negative 5 minus 4 is 1. 1 is positive. Negative 5 minus 4 is negative 9. Sorry, that's negative. Negative 5 minus 4 is negative 9. That's negative. Next, plug negative 5 into the denominator. 2 times negative 5 is negative 10. Negative 10 minus 3 is negative 13. Negative 13 squared is positive. When we square, negative number become positive. Next, plug negative 5 into the denominator. Negative 5 plus 4 is negative 1, which is negative. Then, multiply and divide. If there are even number of negative signs, for example, 2 negative signs, 4 negative signs, or 6 negative signs, if there are even number of negative signs, when we multiply or divide, answer is positive. If there are odd number of negative signs, for example, one negative sign, 3 negative signs, 5 negative signs, if there are odd number of negative signs, when we multiply or divide, answer is always negative. Next, plug in negative 2. If we plug in negative 2 for x, 4 times negative 2 is negative 8. Negative 8 plus 5 is negative 3. Negative 3 squared is positive 9, which is positive. Next, plug in negative 2. Negative 2 minus 4 is negative 6, which is negative. Next, plug in negative 2 here. 2 times negative 2 is negative 4. Negative 4 minus 3 is negative 7. Negative 7 squared is 49, which is positive. Next, plug in negative 2 here. Negative 2 plus 4 is positive 2, which is positive. There's only one negative sign, so when we multiply or divide, answer is negative. If there are odd number of negative signs, when we multiply or divide, the answer is negative. Next, plug in 0. If we plug in 0, 4 times 0 is 0. 0 plus 5. 0 plus 5 is 5. 5 squared is 25, which is positive. If we plug in 0 here, 0 minus 4 is negative. Plug in 0 here. 2 times 0 is 0. 0 minus 3 is negative 3. Negative 3 squared is positive 9, which is positive. Plug in 0 here. 0 plus 4 is 4, which is positive. There's only one negative sign. If there are odd number of negative signs, when we multiply, answer is negative. Next, plug in 2. If we plug in 2 here, 4 times 2 is 8. 8 plus 5 is 13. 13 squared is 169, which is positive. Plug in 2 here. 2 minus 4 is negative. Plug in 2 here. 2 times 2 is 4. 4 minus 3 is 1. 1 squared is positive. Plug in 2 here. 2 plus 4 is 6, which is positive. There's only one negative sign. If there are odd number of negative signs, when we multiply or divide, answer is negative. Next, plug in positive 5. If we plug in 5 for x, 4 times 5 is 20. 20 plus 5 is 25. 25 squared is a large positive number, so we know it's positive. Plug in 5 here. 5 minus 4 is 1, which is positive. Next, plug in 5 here. 2 times 5 is 10. 10 take away 3 is 7. 7 squared is positive. Next, plug in 5 here. 5 plus 4 is 9. 9 is positive. Then multiply. When we multiply or divide only positive numbers, the result is always positive. Next, let's test the end behavior over the horizontal asymptote. Next, let's test the end behavior over the horizontal asymptote. We plug in some very large negative number and some very large positive number. If I plug negative 100 into function f, we plug in negative 100 for each x. Then calculate this. Since we can't do this manually, let's use calculator. If I plug in negative 100 for each x, use calculator. In my calculator, I get 4.102. If I plug negative 100 for each x, I use calculator, I get 4.102. If I plug in some very large positive number, I can plug in 100. If I plug in 100 for each x, if I plug in 100, and I use my calculator, I get 3.901. Now, based on this information and this information here, let's sketch the graph. Let's graph the asymptotes first. Asymptotes and zeros first. Graph the asymptotes and zeros first. Horizontal asymptote is y equal to 4. One, 2, 3, 4. Assume 4 is here. We draw dashed lines for asymptotes. This is a horizontal asymptote. This is a horizontal asymptote. Vertical asymptote is 3 over 2 and negative 4. 1, 2, 3, 4. So negative 4 is here. That's a vertical asymptote. That's a vertical asymptote. Another vertical asymptote is 3 over 2. 3 over 2 is about 1.5. 1.5 is somewhere between 1 and 2. So that's 3 over 2. That's another vertical asymptote. Next, let's label the zeros. The zeros is negative 5 over 4 and 4. Negative 5 over 4 is about negative 1.25. Negative 1 is here. That's negative 1.25. This is negative 5 over 4. Another zero is 4. 1, 2, 3, 4. That's another zero. So those are zeros and asymptotes. Next, let's sketch a graph based on this information here. When x is less than negative 4, function f is positive. Positive means it goes above x-axis. When x is less than negative 4, function f is positive, which means it goes above x-axis. So function f is above x-axis, and function f must get closer to both asymptotes. Function f must get close to both asymptotes. This is a vertical asymptote, this is horizontal asymptote. So the only possibility is that it may look like this. That's one possibility. Or it may look like this. It may go through the asymptote, then approach from below. There are two possibilities. It may approach to asymptote, horizontal asymptote from above. Or it may go through the asymptote first, then approach from below. There are two possibilities. But here we know that f of negative 100 is 4.102. That means when x approaches to negative infinity, function f is above 4. When x approaches to negative infinity, function f is above the horizontal asymptote. So it's this case. Function f approach to 4 from above. Since when I plug in very large negative number, function f is above 4. So function f approach to 4 from above. Function f approach the horizontal asymptote from above. That's the first piece. Next, when s is between negative 4 and negative 5 over 4, function f is negative. That means it goes below x-axis. When s is between negative 4 and negative 5 over 4, function f is negative. That means the curve is below x-axis. So this is a zero. Start from this point. The curve is below x-axis, and that's a vertical asymptote. The curve must get closer to the asymptote. The curve must be very close to the asymptote. That's the graph. Next, when s is between negative 5 over 4 and 3 over 2, function f is negative. That means function f is below x-axis. And we know that this is a vertical asymptote. The curve must get closer to the asymptote. The curve must get close to the asymptote. This is a vertical asymptote. The curve must get very close to the asymptote. Next, when s is between 3 over 2 and 4, function f is negative, which means function f is below x-axis. So when s is between 3 over 2 and 4, function f is below x-axis. This is a zero. Start from this point. Function f is below the x-axis, and the curve must get. This is a vertical asymptote. The curve must get very close to the asymptote. Next, when s is more than 4, when s is greater than 4, function f is positive. Function f is positive means it goes above the x-axis. so it goes above the x-axis. Now, this is a horizontal asymptote. The curve may approach the asymptote like this, or it may go through the asymptote, then approach from above. But we know that when we plug in very large number, when we plug in very large positive number to function f, we get 3.901, which is below the horizontal asymptote. Horizontal asymptote located at 4. 3.901 is below the horizontal asymptote. So the curve approaches to 4 from below. 3.901 is below 4. When we plug in very large positive number, it's below 4. So know that the curve approaches to this horizontal asymptote from below. And we know that the graph of rational function is always smooth. Let's fix the curve, make it smooth. Let's fix the graph, make it smooth. The graph of rational function is always smooth. It may not be continuous, but it's always smooth. There's no sharp angles. So that's a rough sketch of this rational function. That's a rough sketch of this rational function, y equal to f of x. Next, let's find the intercepts. Now, S-intercepts is the zeros. The S-intercept is the zeros. Negative 5 over 4, comma 0, and 4, comma 0. For the Y-intercept, we plug in 0 for x. For the Y-intercept, we plug in 0 for x. So y equal to f of 0, which is 4 times 0 plus 5 squared times 0 minus 4 over 2 times 0 minus 3 squared times 0 plus 4. Then simplify. 4 times 0 is 0. 0 plus 5 is 5. 5 squared times 0 minus 4 is negative 4. On the bottom, 2 times 0 is 0. 0 minus 3 is negative 3. We get negative 3 squared times 0 plus 4. 0 plus 4 is 4. Then multiply. 5 squared is 25 times negative 4. 3 squared is positive 9 times positive 4. 25 times negative 4 is negative 100. 9 times 4 is 36. We can divide top and bottom by 4. I get 25, negative 25 over 9. So here, y equal to negative 25 over 9, which means the y-intercept is 0, comma, negative 25 over 9. Since we didn't draw the y-axis in scale, so just label this point negative 25 over 9. This point here is negative 25 over 9. That's the y-intercept. That's an S-intercept. Negative 5 over 4 and 4. That's an S-intercept. That's the Y-intercept. Next, let's find asymptotes. Horizontal asymptote is y equal to 4. Vertical asymptote is s equal to 3 over 2 and s equal to negative 4. So the horizontal asymptote is y equal to 4. Vertical asymptote is s equal to 3 over 2 and s equal to negative 4. That's an horizontal asymptote and those are the vertical asymptote. Next, let's find end behaviors. We have end behavior 1, 2, 3, 4, 5, 6. There are 6 end behaviors here. For the end behavior, as x approaches to infinity, as s approaches to infinity, we can see that as s approaches to infinity, the curve approach to 4 from below. So f of x approach to 4 from below. Negative sign means it's a little below 4. This little minus means it's a little below 4. As x approach to negative infinity, as x approach to negative infinity on the left side, the curve approach to 4 from above. It's a little above 4. So f of x approach to 4 from above. Next, let's find end behavior near negative 4. Next, let's find end behavior near negative 4. As x approach to negative 4 from the left, as x approach to negative 4 from the left, negative 4 from the left, we can see that the curve goes all the way up. So f of x approach to infinity. As x approach to negative 4 from left, f of x approach to infinity. As x approach to negative 4 from the right, as x approach to negative 4 from the right, the curve goes all the way down. So f of x approach to negative infinity. As x approach to negative 4 from the right, as x approach to negative 4 from the right, the curve goes all the way down. So f of x approach to negative infinity. Next, let's look at end behavior near 3/2. As x approach to 3/2 from the left, as x approach to 3/2 from the left, that's left side, that's right side. As x approach to 3/2 from the left, the curve goes all the way down. So f of x approach to negative infinity. As x approach to 3/2 from the right, the curve goes all the way down. So f of x also approach to negative infinity. As x approach to 3/2 from the right, f of x approach to negative infinity. As x approach to 3/2 from the right, f of x approach to negative infinity. It goes all the way down. Those are the end behavior of function f.